Can everyone see my screen? Yep. Okay.
Yeah.
So good morning, good afternoon, everyone. My name is Chien. I'm the regional head of marketing. Thank you very much, NACE FMS Malaysia, for giving me the opportunity to talk today. Today, we will be talking about how to accurately size corrosion, as the title suggests. And today's talk will be an interactive talk. So if you guys would like to participate, you can either scan in the QR code or you can just go to your web browser and just type in ahaslides.com/QSR1. So I thought I'd change things up a little, make your Friday afternoon a bit more exciting so that people don't fall asleep. I myself am having a cup of coffee. He'll give about 30 seconds for everyone to come in. Yeah, so for those of you who are already in, I think there's 11 people on this interactive software. So first question, are you ready, guys? Just to get everyone warmed up to get used to the interactive session. Okay. So just a quick one. How did you guys hear about this event today? Is it through LinkedIn, email, referrals, or websites? Okay, we're getting a lot of people hearing it from LinkedIn, referral. Okay, interesting. Seems like LinkedIn is very popular these days. Okay, great. So just to introduce myself again, so I'm the regional head of marketing for Guided Ultrasonics Limited, UK. So I'm currently based in our Malaysia office here in KL. My background is mechanical engineering. My background is chemical engineering from Imperial College. And I also did my PhD in mechanical engineering. I'm also a level 2 inspector in guided wave testing, and I have more than 6 years in this technology. So an introduction to Guided Ultrasonics Limited, or GUL. It's a UK-based company in London, and they specialize in the manufacture and research and development of ultrasonic guided wave technology, mainly for pipeline inspection. They are an instrument and equipment manufacturer, and like I said, their strength lies in research and development of the technology. So GUL holds many patents in this field. They are the inventors and pioneers for area inspection using guided wave technology, which has found its place in the oil and gas pipeline inspection services. And they have an unparalleled 30 years of experience in this, both in this technology and also in the field. A bit of background about the solutions that GUL offers. So it can be split into 4 categories. So the first one being screening, which offers a fast way to detect corrosion in pipes. Secondly, we have monitoring, which leverages on the same sort of technology, except the sensors are permanently installed, so you can monitor your pipeline over a long period of time. We also do subsea pipeline inspection. And finally, we have scanning, which is focused on sizing corrosion accurately at pipe supports. So this will be the theme of the talk for today. We have a global presence in over 50 plus countries. We have more than 5,000 systems deployed, and we have more than 250 customers across the world. So just to get me familiar with the background of the people in the audience today, are you guys service providers, asset managers or owners? Do you own pipelines? Or are you representing an equipment manufacturer? Or none of the above? So I assume others are probably the NACE people. Okay, so just to give a bit of insight into the people. So yes, quite a few asset owners and service providers. It looks quite balanced. No equipment manufacturers here, apparently, based on our 15 people. Okay. Right, so for those of you who are here, I'm sure you know what is corrosion under pipe support. You know, do you think it's A, B, or C? Oops, open. Yeah, there you go. Yes, pretty obvious. I think everyone here who are members of NACE or non-members of NACE are quite aware of what corrosion under pipe support is. A being just a localized pitting type of corrosion, and C being CUI. A bit of background on corrosion at pipe supports. So typically it occurs because of the formation of a crevice due to the curvature of the pipe at a flat surface, and water gets trapped at this crevice or the space between the pipe and the support, and we get coating of the pipe that begins to fail, and eventually corrosion happens, which leads to wall loss in your pipe. Okay, and this has a devastating effect in the industry. So for example, a classic example would be what happened in Sunoco refinery in the States in 2009. There was a serious cups defect in their 10-inch pipe. They had a breakout of a 24 hours fire, and eventually leading to more than $50 million in losses. And as most of you know, cups is a very expensive problem that the industry have. It's part of the billion-dollar problem, as quoted by NACE. And so my question to you guys here today is how, what is your level of concern with cups? How much cups do you typically encounter on your site if it's relevant to you? And how severe are your these damages in your pipes, and how concerned are you? So 1 being not concerned and 5 being severe. So looking at the data here, generally looks to favor the right hand side. So it means that a lot of people here today are here because they are they have some sort of concern with regards to cups. Okay, wonderful. So now going to the inspection of cups, the first stage with any inspection of any types of defects in your asset is detection. So detection means being able to locate it and tell that there is a problem at that location. Okay, and the two methods that we'll be talking about today, or we're going to mention, the first one being the most powerful one, which is visual inspection. So using your eyes and doing a walk around your site, you can when it comes to cups, it's clearly one of the fastest and affordable way to detect corrosion under pipe supports. Okay, and the second being guided wave screening, or LRUT, which involves using guided waves, attaching a sensor onto the pipe and transmitting ultrasonic waves along the pipe. And the beauty of it is that your results are digital, and you're able to process them and detect cups. So for example, there was cups detected roughly about 2 meters from the ring based on this data. Okay, great. Now you found your corrosion under pipe support. What do you do next? Well, the next thing you need to do is to be able to size the corrosion so that it will enable you to carry out fitness for service assessment, example being ASME B31G. And here lies the problem, or the challenges when it comes to sizing cups. The first one being that the support just gets in the way, so you cannot have direct physical access to the bottom of the pipe. The second one being that it's a non-uniform defect. That means that you can get, let's say at the 5 o'clock section of the pipe, you may only be getting a 10% wall loss, and at the 7 o'clock section of the pipe, you may be getting a more severe wall loss, such as nearly half of the remaining wall thickness left. Okay, and the third being when it comes to deploying sensors that attaches itself onto the pipe, you have unpredictable surface properties because the properties of these pipe coatings, for example, will vary from site to site, from location to location. So these type of things can pose a challenge to the inspection industry. Just a quick quiz on what is the main challenge in sizing cups, just so that you guys are still awake. Okay, 3% is still awake. 4, great. Okay, 5, good, yep, good. Everyone is still awake, great. Okay, so today we'll be focusing on sizing corrosion under pipe supports using ultrasound or guided waves. So guided waves is a form of ultrasound. And typically the advantage of ultrasonic techniques is that we're able to overcome the first limitation or the first challenge when it comes to sizing corrosion under pipe support. And that would be because you can inspect it indirectly. This means that we have a transmitter and a receiver that is away from, that is in an accessible location, such as the top section of the pipe. And you can transmit your waves circumferentially around the pipe. There are a couple of examples of techniques that utilizes a form of ultrasound within the pipes, such as the 5 listed over there. A couple of photos of the MRUT method by Inaspec. And typically, we would use the amplitudes of the signal that we receive to deduce whether or not a corrosion has been detected and sizing the corrosion. So the next slide gives you an illustration of what the signal would look like if you have a setup like this. So you would on your this signals on the right is showing the signals that your receiver is picking up. So if you focus on the top graph, you see the signals from a good piece of pipe where there's no defect. Okay, and on the bottom one, you would see signals from a corroded pipe with cups. And what you can notice is that I've just highlighted the peak amplitude for the second packet of wave, and you can see that the difference in both of these cases is a drop in amplitude. And typically, amplitude-based methods would relate the change in amplitude to the severity of the corrosion. Okay. And the problem or the challenge that amplitude-based analysis poses is that, this amplitude change that I've just shown you, they are also, not just affected by the corrosion, but they're also affected by for example, the shape of the defect. So if the defect is very shallow and wide, then you may get a different type of reflection. And if you have pipe coatings, you may lose signal energy or amplitude to pipe coatings. Okay. And secondly, no defect specificity. So that means that if you look at the diagram in the middle, you can see that this pipe has 2 defects, one being a shallow one and one being a deep one. So an amplitude-based analysis would typically give you an amplitude measurement, but not be able to differentiate between one from the other. And finally, when you use amplitude as your reference to sizing, then you are very prone to calibration sensitivity. So if your calibration is wrong, so if your 100% signal, for example, is incorrect, then the rest of your results would be inaccurate. Okay. Just a quick quiz on what is the challenge with amplitude-based analysis. Why amplitude is a problem? Yeah, so this slide is just to make sure that everyone is on board with what I was just saying. So the right answer is actually the first one, which is it can be affected by many other external factors. So you can measure amplitude. It's not particularly difficult to measure amplitude, but the problem is, in some cases you may get poor signal to noise ratio. So maybe that's what you're thinking of. Okay, but measuring amplitude is, if you have a receiver and it's coupled onto the pipe correctly, then you can measure it. I think signals are too complex. That is partially correct as well. But most importantly, amplitudes of the signal can be affected by many other factors, such as the shape of the defect, the paint, which absorbs the energy, and many other factors, and also calibration. Okay, so here at GUL, we have developed the QSR1, which uses the same principle of having your transmitter and your receiver on the top section of the pipe. Okay, but the difference is that we go beyond standard amplitude-based analysis so that our sizing capability is accurate. And this is the main section of the talk, which is focused on being quantitative, because our measurements are, gives you a number in terms of thickness readings. So no, we don't focus on the signal amplitudes. And we use a frequency-based method, which we'll cover later, which gives it its accuracy. And the reliability comes from it being a semi-automatic scanner. Okay, so we focus on giving measurements such as this plot that I've shown over here, which is a plot of thickness against the axial length. Okay. And the two main results that the system gives you is the nominal wall thickness of the pipe and the minimum remaining wall thickness in your pipe section. So in this case, we've scanned about a meter of the pipe, and we found that the deepest point is about 6.35 millimeter. Okay. It operates using guided waves. So we use electromagnetic acoustic transducers that coupled onto the pipe, and we transmit guided waves that goes around the pipe circumference. Okay. And the difference with our method is that our signals are processed using our patented GUL scanning, or a frequency-based method. And using that method, we're able to calculate the remaining wall thickness directly. Okay, we don't focus on the amplitude. So here is an animation that has been sped up to give you an understanding of how the QSR1 works. So you would deploy it on the pipe, and it would scan semi-automatically along the axis of the pipe, and it would give you, as it scans, you are getting the minimum remaining wall thickness and also the nominal wall thickness in real time. Okay. Right. So how does it all work? So basically, we just go beyond amplitude analysis. So we do more or less the same thing. We transmit our guided waves, we receive them. But instead of looking at the differences in amplitude, we focus on studying the signature of the energy, or the frequency spectrum. So we look at the frequency contents of our waves, and using our guided wave mathematical equation, we are able to calculate the wall thicknesses directly using the information from the frequency. So if you see this equation over here, this little complicated equation, you can see that I've highlighted in red frequency, and I've highlighted in green thickness. Okay, so essentially, once you know frequency and the other parameters, then we are using it to calculate wall thickness directly. All right. So an analogy to help you guys visualize what is going on. Just imagine that you have a wine glass or a glass of water, and you have it full or relatively full, and you start rubbing your fingers against the edge of the glass. You would generate a low frequency sound like And this is analogous to a good pipe. Why? Because we use the frequency of the sound to tell us that, okay, the pipe is good. All right. So in contrast, if you have a pipe that is damaged due to cups, then the frequency of the sound becomes higher. So imagine if it was a cup, you go. So that is the difference between, you know, low and high frequency. Okay. So the pitch of the sound has changed. And that is the a basic principle of how the QSR1 operates. So we measure the thickness based on frequency rather than signal amplitude, okay? And then just summarizing again why you know, frequency-based analysis is more accurate, because when it comes to different corrosion profile, unlike signal amplitudes, which can get a bit, which may look the same for both defects that I've shown over here, using a frequency-based approach, we can tell you what the deepest defect is, and we can differentiate it from, you know, a 40% localized, very localized, very narrow defect compared to a flat or a wide 10% wall loss defect. Okay, that is the difference. And then when it comes to being affected by signal energy losses, so energy losses can occur when the waves of your energy gets absorbed by the surroundings, such as liquids or your support pads or your paint or your any type of coatings or linings. So that would affect your signal amplitude. But when it comes to looking at the frequency content of it, that would be negligibly affected. So just a quick show of who has been staying awake and what did you get from, you know, why is frequency analysis being more accurate? Okay, great. So it looks like people are paying attention. So yes, the middle, the B is the second one is the correct answer. So it's not about signal length or which one is bigger. It's about, you know, because we can correlate frequency directly to thickness. And that is the beauty of frequency-based methods, okay? And of course, the QSR1 has been developed since 2017. It's a fairly new product among our, you know, 30 years of history in guided waves, but it has been strongly validated independently. And such as shown here, we're actually, we have a ex-service pipe, a pipe that's been removed from service with real corrosion under pipe support, okay? And because it's been removed, we are able to use other techniques such as laser scanning to accurately measure the remaining wall thickness. Just note that, you know, you cannot laser scan in service pipes because of inaccessible. So we are only able to do this because we've basically cut the pipe out, okay? And we are comparing, we've compared the results to using the QSR1, and we found the accuracy to be between plus or minus 0.5 millimeter. Okay, so here is a real case study on a 10-inch diameter pipe. It's a jet fuel line and with a lot of supports, as you can see in the photo, all right? And sometimes visually, it can be hard to detect cups. It's not impossible, but you know, you have to evaluate your probability of detection. If it's a dark day or there's not enough light, like in the UK, you don't have, you know, they've never seen the sun before. So you would have to, you know, depend on other methods like guided wave screening to be able to, you know, tell you and digitally record if there's any problems with at the support locations. Okay. And just going into a bit of details here, you can see that you've got two types of signals: the black trace and the red trace. Okay, so you can tell that we know that there are two cups location here because of the higher red trace signal compared to this location where the clean support is. So that is that is how we would detect corrosion under pipe supports using GUL screening or guided wave screening. Okay, and as I said, the first stage is detection. Now it's to move on to sizing. Okay, and with sizing, we use the QSR1 and we scanned over each of those supports to measure the remaining wall thickness. So an inspector would go on the site, they would attach the QSR1 onto the pipe, and you would get a graph such as shown here on the right. Okay, and from that you can quantitatively and confidently tell that the remaining wall thickness is 70%. Okay. Here is another case study on a 12-inch oxygen line. It's quite a thin pipe. It's a 6 mil nominal thickness pipe. And what this client has done is that they have lifted the pipe to validate our QSR1. So they have plenty of these support locations, but they have to, the client wanted to be confident with our QSR1. So at certain locations or one location, they have lifted the pipe and tried their best to measure the remaining wall thickness using a very old school method of just placing a ruler there. Okay, and comparing both of these results from the ruler, you can, if you zoom in real close on our high resolution photo, it is roughly about 3 millimeters. You just have to believe me on that. I don't think you guys can see it from here, but using our QSR1, we get more or less the same set of results. Okay, so what this is telling us is that there is the worst possible measurements on this pipe is a 50% defect, which is very severe. All right, so we are wrapping up now. So how do you guys feel about using QSR1 to size the cups, or do you prefer? Do you have other types of methods? Because I know there's a bunch of inspection service providers here in this talk today. Do you guys, yeah, okay, good. I'm doing a good job at marketing, I suppose. So one guy doesn't want to use it. That's fine. All right. And, at GUL, we're always developing and continuing our research. We're expanding our application. So right now, the limitation with the QSR1 is when it comes to locations or support locations where the QSR1 is unable to move across, such as at clamp supports. So basically having that U clamp over there stops the QSR1 from being able to move across it. Okay, and but this year we will be launching our add-on sensor to the QSR1 that uses the same sort of technology, but instead having a standoff. So we're able to expand the application to clamp supports or any other type of supports that hinders the movements of the conventional QSR1. And also we are able to perform inspection at interfaces such as soil air interface or a concrete air interface and so on. So today I'm working from home today, and there wasn't enough time to give a demonstration of the product, but we will be doing a live demo of our product, and there will be one of our leading expert and a veteran in NDT who will join us in our talk. And this will be on the 8th of April. So if you guys are, those who are interested in the QSR1, you can watch a live demo so you can see how we would assemble the equipment, how fast it can be assembled, and how we would put it onto the pipe, how we would use the software to set it up, and how fast does it actually move in real life. So this, if you are interested, then join us in the next talk. Yes, so we are done. So that's the end of my talk. So thank you very much for those who were participating. I'm glad that some people have joined in and played along with the quiz.
Thank you, Dr. Chua, for having a very informative knowledge sharing session on the GUL scanning application on the cups. So, okay. So now we will move on to the next session of the evening on the Q&A. So I'll just pick the question from the chat box. Okay, the first one. Does the piping operating temperature and pipe coating affect the measurement accuracy? Dr. Chua, hand on to you.
So the temperature does not affect the measurements, but we have a temperature range, so you cannot operate outside of our temperature range. I believe it's 70 degrees Celsius. That's the higher end of the range. So the reason for that is because we use magnets. So magnet properties are affected above 70 degrees in our case. But if you were to measure it at 50 degrees or 20 degrees, the accuracy would be the same. Just to add on, you said something about pipe coating as well. I'm looking at the Zoom chat as well. Pipe coating, so we can tolerate most type of coatings. As far as we believe, we've never had problems with the type of coatings, less like paints, etc. But the thickness matters. So we cannot inspect. We can inspect thicknesses from 1 millimeter and below. If you have any pipes, which is common, you can find some pipes with thick paint. Then you would focus on some surface preparation at the location of the transducers only. So you don't, for example, remove the coating of the entire pipe. You just focus on where the transducers will be running over.
So I think the next one will be, what is the minimum and maximum pipe size possible?
Minimum and maximum pipe size at the moment, we cover 6" to 24" in nominal pipe diameter. And in the future, when we have our axial sensor launched, that will cover a much wider range of pipe sizes.
How about will the effect high noise surrounding affect the inspection?
No, because we operate within a strict range of frequencies. So unless the noise is very specific to to the range that we're inspecting, which is almost impossible or rare, then no, it will not have any effect.
Okay, I think we don't have any more. Okay, is it work for clad pipes or CRA pipes?
I believe no, but I'll have to check on that. I don't think this is applicable to cladded pipes. No, I mean my answer would be no. There are also a bunch of questions in the slide as well.
Hand over, yeah.
I'm just going to address Azdariadi's question. Yeah, is it affected by thick coating? Like I said, it matters. So we'd have to, the accuracy will not, but in order to get good coupling between the transducer and the pipe, your coating needs to be up to only 1 millimeter thick. So any thicker, then the problem is getting the energy into the pipe, not the accuracy of the signal. Is it possible to measure cups on welded supports? The answer is no. We are focused on simple supports where it's resting, not welded. So this would not work for welded supports at the moment. So we are looking into expanding our application to that. But thank you for the question, Zavi. Shazwan, how frequent cups inspections in a certain plant or factory? I think so. I'm not an inspection company. I don't represent an inspection company. We are a manufacturer of equipment, so that would depend on your inspection. Maybe some other people can give some comments on that. But to me, I think if it's severe, if you have, it's all about the rate of the corrosion. If the corrosion is happening, at 0.5 millimeter a year or 1 millimeter a year, then and you have a thick pipe, then that frequent cup inspections can be not so frequent. But if you know that your corrosion rate is high, then you probably want to inspect more often. So you would want to use the QSR1 and size it every 1 month or every 2 weeks or something. It depends on your corrosion rate. Mr. Singh, if the pipe have high flow rate and induced noise, does this affect the result or sensitivity? Again, it depends on, I would say that if the pipe was vibrating violently, then I think that would affect it would affect the results, because the transducers would not be secure. But if it's just to do with noise and there's no serious vibration on the pipe, then no, the results will not be affected. The sensitivity will not be affected. Will the new axial tool be able to measure minimum and average thickness as accurately as the QSR1? So this capability is currently being validated in the field. So we are conducting field validations in the UK on a real site. So we've done all our lab trials, and now we are validating it on real corrosion. So I won't be able to answer that question. I would like to believe so, but we are using the same GUL scanning method. So the scanning, the signal processing has not changed that much. So we would hope that the accuracy would be just as good. Another question by Singh: Is there any limitation on the external coating type and thickness, thermal spray coating? Generally, no, there's the type of the coating does not affect it. But then again, we would have to, if you have something very specific, then you would have to let us know. But generally, most type of paint will not affect it. But of course, if the pipe is wrapped with bitumen or concrete, for example, then that will be a problem. Is your technology accurate for small remaining thickness levels? Small, you mean that if there is a very, very, very severe wall loss? So the accuracy of our technology is high when there's a high remaining wall thickness, but as the pipe wall gets, damage gets very severe in the order of like 70% or 60%, 70% and above, then the accuracy of the system drops from 0.5 millimeter to 1 millimeter. So it becomes like you are saying, it becomes a bit less accurate. Does the QSR1 provide a circumferential extent measurement of the corrosion? So that will be what the axial sensor in the future will offer. So it will be able to measure or plot the remaining wall thickness around the circumference. I think that's your question. If the pipe internal fluid tend to have deposit, is the QSR1 suitable? So I think it depends on the level of the deposit. If the entire pipe is full with deposit, then I believe that will be challenging because the attenuation of the signal would be very great. But if there's a little bit of, as long as there's some signal to noise, then we would be able to account for this type of application. So a good gauge is, to use if you can UT your pipe and get signals, then it's a good gauge that the QSR1 can be used, because if the ultrasonic attenuation using high frequency UT is still okay, then QSR1 will do better because we are using a much lower frequencies. So yeah, so what I'm saying is that you can use UT, for example, to determine if there's attenuation or not. But the problem is attenuation. Is QSR1 able to scan long distances, or is LRUT done with a different device? So the scanning is relatively slower compared to LRUT, because so our screening technology is able to scan hundreds of meters of pipe within a few minutes, whereas the QSR1, because we are focused on accuracy and sizing, it is not built to scan very long distances such as, you know, what maybe you're thinking about pigging. So it's not comparable to pigging. LRUT or screening, yes, that is done with a different device. So you wouldn't use the QSR1 to do screening. And I think any more in the chat?
Yeah, we have here, yep. Any similar technology for checking the pipe thickness or corrosion for subsea pipelines, if it's relevant to answer?
Subsea. So at the moment, the QSR1, we don't have a QSR1 that works underwater at the moment. But if you are interested in that, then feel free to approach us. But we don't have a subsea QSR1 at the moment.
Okay, the next one. What is the present QSR1 product range in terms of diameters covered, like 2-inch to 16-inch?
This is the similar question as before. This at the moment it's 6-inch to 24-inch in diameter, and in the future it will be for a wider range of pipe diameters, possibly up to also 60-inch.
Okay, the next one. Can your system detect the cracks? If yes, what is the smallest crack width and length can be detected?
So our system will not reliably detect cracks. So we don't claim that we can, you know, detect cracks with a very high POD. We are focused on corrosion, and generally it's mainly due to the wavelength of the waves that we are using. So sensitivity of detection is governed by, you know, the frequency of inspection. So the minimum or the reliable size that we can detect is down to about 1 inch. 1 inch by 1 inch is our, you know, limitations in terms of truly reliable data. So anything like a very small pit or cracks, we won't be able to practically or reliably detect it or size.
Okay, Dr. Chua, we can entertain another last question.
Yeah, sure.
Before we end the session,
yeah,
sure. You may select that.
Well, there's only two. I can just do both quickly.
Yep.
So what is the sensitivity of thickness? Typically, it will be 0.5 millimeter, so plus minus 0.5 millimeter, Mr. Wei Jing. So, and Sridhar, can you show a final reporting of the QSR1 system in the test line? Yes, if you want, you can actually send me an email after this, and then I can, you know, send you an email back. But that's not a problem at all.
Okay, thank you, Dr. Chua, for entertaining all the during the Q&A session. Thank you, everyone, for dropping the question as well.